Okay, that was a very good session in the morning. Thanks for that. And let's get into the buzzword of the world, AI. It was actually good to hear something that was non-AI. It comes from a guy who's going to talk about AI. Okay, um, this is about AI, but not that we are doing in offers or in any projects, right? It's a little different perspective. Um, okay, so have you heard about this book called Sapiens? Have you read that book? Okay, Sapiens is a very good book. It gives a different perspective of the world. There's this one chapter where he talks about wheat, how wheat dominated humans, not the other way around, right? So, so wheat dominated humans. It it made it in such a way that the civilization strives around it, thrived around it. So it's a kind of a different perspective if you read that chapter particularly. I think the same thing is happening in AI also, right? It is redefining everything, right? In software industry, 10 to 15 years back, especially in programming, function programming turned the tables. It came back with Scala and Clojure, and there was one language called Ceylon by IBM. It was a very good one, but it didn't thrive. I thought it will go to the next level. I thought Haskell will become mainstream, but again, Rust came. I thought Rust will become mainstream. After functional programming, I thought dependently typed languages will come to the limelight, but again, it fizzled out, right? And then AI came. It overtook all these things, right? Um, and as I said, like how wheat dominated humans, I think AI is turning the tables now, and it has gone into all the industries, almost all, not everything, right? So, so there's a kind of a different perspective. Whatever most of the jargons, I'll try to clear it out. But whatever I'm going to share is my. It's not, let's say, intelligence. That's our intelligence, right? It's not about the model or the AI as intelligence as an AI. It is our intelligence. How our thinking and our intelligence is changing in the AI world. That's what I want to share. But now, why this thought came? Sometimes back, some couple of weeks or months back, there was a guy shared a no-code library called Venword. Okay. Now, no, this Venword doesn't have any code at all. We talk about all the vibe coding, no code, low code, less code, whatever it is, right? It is typically that. Right? There's no code at all. It only has spec. It is just a very tiny library. I think something related to time conversions or something related to time, but there is no code at all. There's only spec. The spec also has instructions for testing, all those things. All uh, concepts that is required to create a library. Now you can take that spec, feed it to your LLM, pick your language. It can write the code in your favorite language using that spec. It can also write test cases, and then you can start using that as a library. Right now, if something happens, like there is a bug, and how do we do an RCA on it? Let's say we usually do RCA, right? When there is some bug in the production, and we make the systems available for the users. That's the first thing that we do. But we do an RC. When we look at the bug, we know in where in the system the bug is likely to be placed. We go there and again we write test cases, solve it, fix it, and push it. In this case where there is no code library, when something like this happens, what is the procedure? What are we going to do? How are we going to solve that? How are we going to fix that bug and release it? So that's when this came. Like I think our entire human intuition, like the developer's intuition in code, is changing, right? When you know a bug, when you see a bug, you know, okay, this is the line. Something has happened in the if-else condition. This if is not evaluating this condition. That's why there might be a bug there. We know because we wrote the code and we know what is happening in the system. Sometimes we even know there's going to be a bug, right? We know where the bug is going to be, but for some reasons we still push it because high priority, low priority, all those things comes into picture. But when it comes to AI powered systems, how are we going to solve that? How are we going to approach that? And when I say AI powered systems, it's both using AI to write code and AI infused systems where you use LLMs models inside the product itself, right? Like DevOps agents. Like we are, I think AWS and GCP, they have their own DevOps agents and gives you lots of features. Um, so that's what triggered this thought, and I started writing, right? And it is not working. Okay, so as I told you, this is not about any tools. There is no prompt sharing. I'm not going to do any prompting. Probably we'll see a example, but it's a very naive example. But this just a knowledge sharing or thought sharing, right? It's specifically, um, I will talk more about the ambiguities that rise in these systems. So, distributed intelligence. So, why intelligence becomes distributed in AI powered systems? Because intelligence resides where the reasoning is. Again, reasoning, I'm not talking about the model's reasoning, our reason, where we go and reason about the code or any of those artifacts, right? So intelligence lives where the reasoning is, and the reasoning lives where the boundaries are. And these boundaries are distributed, right? The boundaries might be in the code, it can be in the prompts that you use, it can be in the models, it can be probably in other validation layers, or it can be in other developers or other humans in the system that's using the whole system. So the reasoning is spread across all those layers. When we're talking about layers, now even the horizon has spread, right? Earlier, it used to be uh, a developer thinking about a feature. He thinks in his mind how to implement it, writes tests, writes a code, and push it to production, and then there is a path to production. Now it is slowly changing. First, we think what prompt to write, and then how correctly write it. One of uh, one of the thought workers shared that we should go back to Ren and Martin and read much better grammar to actually instruct the prompts because it always misunderstands and the other hallucination starts happening, right? So the layers has expanded, the horizon is expanding, so there are many layers now. That's why the ambiguity also arises. We don't know where the ambiguity is arising, whether it is in the prompts, whether is it in the code, or is it in any other layers. It's just not the prompts layer, right? There is a reasoning layer also. And now we have thinking layer, we have reasoning layer, and what's going to come, we don't know. So So the ambiguity so raises in those places, right? So ambiguity can be anything. Uh, let's say your let's let's say you have a login form and you get inputs for that form, right? And then we do a validation whether the username is correct. It has some 72 characters or whatever it is. Password is 12 characters length or not. So that's the ambiguity. It is right or not. That's the ambiguity I'm talking about. So, and then once you once we fix on that, what is the correct path? That's where the boundary breaks, and it takes a new path. The path is fixed now, right? So that's the kind of ambiguity that I'm talking about. So before that ambiguity, there might be multiple paths. Once we are the code evaluates the input parameters, validates it, then it takes a determined path, right? So in a traditional software system, like the example that I gave you, if some condition is true, it takes one branch, otherwise it takes another branch, like state machines also. So even these are explicit, right? We know the branches, if else conditions, loops, and all those stuff. And it's enumerable. You can list it up. What are all the branches that we are going to? It's there. And we can probably inspect or debug also those branches, and we can test those branches also, right? So when something fails in those boundaries, we can locally reason there. We can find out what is happening in that place. We know where to look. And uh, for most of the time, this also has been moving actually. Uh, if you see, earlier we had assembly language, then we had C, then we had C++, and we had Java, and the languages also evolved, right? And it made easier for us to write code and reason about it, right? And then we had the deployment pipelines, and now we have CI/CD pipelines where we can go and check where the deployment fails. So we can locally reason there. The ambiguity arises there, we can go and check why that is happening. And we also have schema validations. We have explicit constraints, uh, whether it be types or whatever it is, right? So in the pre-AI era, these were very deterministic. We know what is happening, where it is happening, right? But when LLM is involved, whether in an AI infused product or using it for developing a code and writing code, the runtime ambiguity is coming back because the decision points are many now. There are many decision boundaries, right? Again, prompts are thinking, the prompts converted uh, into the model, and the model again uses RAG to get data, stores it in vector databases, and then retrieves it. There is some prompt expansion is happening, injection is happening. So when some ambiguity arises in the code or in the decisions, it is now becoming difficult to actually go and where to reason about it, right? So what happens in LLMs usually is there's a very naive one concept that I picked, but it's a main concept in LLMs, right? It's a probabilistic inference layer. Uh, this is how LLMs actually generates response for us, right? So it takes a token and then it finds the next possible token. So that's how it gets us answers because it's all probabilistic in the system because um, It has a training data. The training data is stored in vector databases, and then it chooses the closest one to the word that is residing there. It's all about weights and temperature and all those stuff, right? And this increases the ambiguity of uh, the code also, right? And the decisions that is being made. Uh, so I talked about this already. So we have two AI powered systems. One is where the LLM writes code, or we use models to make decisions. Let's see how this ambiguity resides in the boundaries, how it is breaking, how it is not changing, or how it behaves. For example, let's take a very naive payment system, right? You have a payment coming in or a transaction coming in, and you have to handwrite or handwritten a microservice to determine whether the transaction is a valid one or not. So what we will do, like basic validations, the amount should be positive, it should not be negative, it should not be zero, all those things. It should be a supported currency, um, the maximum amount, minimum amount, all those things comes into picture. So in a handwritten microservices, these are very easy to encode, right? But but the same payment system, we don't write payment fraud detection systems like that, right? There are some third party providers available where we send all the details to the third party provider, and then it determines whether the transaction is correct or not, it's a valid or not, whether the merchant is who raised the transaction is a fraud or not. All these things happens even today, even before AI era, we had those systems, probably a machine learning system or not, I'm not sure. But this happens. Let's take an example as where we are using LLM for this. Now, how an LLM will determine whether the transaction is valid or not? It's more about reasoning, right? It almost thinks like us because they are embedding thinking in the LLM systems. So when this kind of thinking is embedded in the systems, and there are no single LLM models that are being used, right? There will be chain of models being used run parallelly. One will check for merchant information. One will check for the person who raised the transaction, whether that is a valid person or not, the amount, currency, the time, where it is coming from, the credit card checks. Everything happens in parallel. And one of them fails, then it is very difficult to actually go and reason which model failed it, where it is failing, why it has failed, until we have a proper observability on those all those models, and all those observability logs are streamed to another place, and that also has to be monitored, right? So that's how these kinds of ambiguities and decision boundaries are getting spread more, and it is making it difficult to actually reason about the code, right? Or the behavior of the system itself. So just a summary of what I spoke now. So in a deterministic system or a normal microservices, the, the 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 decisions are finite. There is a static reasoning. We know in small places or countable places the reasoning is there. We also do an exhaustive testing, so we have covered most of the edge cases. But in a LLM based probabilistic systems, the decision surface is spread, right? And the verification is based on statistics, probability, not a defined set of rules. In microservices kind of systems, we use defined set of rules or constraints uh, that will help us found the help us in the reason. But in the LLM based or model based systems, the reasoning is based on the statistics, the temperature. Um, it's a probability, right? Right. Okay, this could be the reason this particular transaction is not a valid one. And how the LLM learns, even though there is a very big data set, there is a sampling based testing happens, right? So uh, we provide a basic question answer kind of document to the model to train it, and we keep training it, right? And most of that's the reason there is more hallucinations also. If it doesn't know the if it doesn't have the proper sampling set, it cannot give us a proper reason. That's being solved in many ways, but that is all. This is also one reason. And in AI assisted coding also, so that we talked about uh, the LLM based systems, right? Even in AI assisted coding, sorry, um, the runtime. So the AI writes code. Ultimately, even we write code, AI writes code. Code is code, right? It's going to run. That part doesn't change, right? It is deterministic now. But how the logic ended up in the code, that boundaries has changed, right? As told you before, there's a prompt, and then the prompt goes into the LLM model, and then the model understands the prompt, does some rags, all those things, try to infer what we are trying to ask, and it generates a structure, and then probably we verify the structure again, the output response again, and then it goes in a loop, and then it writes the code, right? Now, at least now we have added 2 to 3 layers than in the human or developer written world, right? So that's where the the ambiguity is happening. Not happening, but if it happens, we have to know where to look for whether the issues in the prompting or in the model reasoning. Now we have started versioning the prompts also, right? So it has become a code artifact now. So we should be able to go back and check whether the prompt is correct, what we have missed. If we add more context to it, can create a better code so that our reasoning becomes better. So why these kinds of ambiguity might arises is because of the invariance that exists in the system. Uh, to give an example of invariance, if you have worked in statically typed languages or strongly typed languages, we can define types, right? Or you define an interface, and there are only 1 or 2 implementations for that, and only that can be used. So the implementations are the invariants, right? Those are determined. Those doesn't change, right? So that is the confidence in the system, right? And then we have validation rules, we have tests, we have architectural boundaries. All these gives a guarantee. Even in invariants, there might be invariants that are implicitly present. It's not explicitly mentioned in the system, in the code. And ambiguity might arise because of those implicitly used invariants also. So all the invariants has to be explicitly mentioned. The more explicitly we mention the invariants, what is going to change, what is not, what doesn't change, what does the system allow, not allow, then it becomes easy to handle the reason. Otherwise, it's going to be catastrophic. And humans in the loop also. So when the humans define the invariance and the LLM models follows that, then when a human in the loop or dev in the loop is there, it becomes very easy to do a code review of that or to debug or to handle the production incidents that comes in. Still, the ambiguity is not removed. It will still be there, but it will be easy to reason about and fix it. So why should we, um, how to bring it up? So LLM written code or human written code, the ambiguity is going to be there. That is, the invariants are going to be there. And once those are listed, we know how to handle the reasoning, right? If the output is going to be the same, then why we have why should we care about all these things? Should we care about all these things? Once we know the invariance and the uh, where the ambiguity might arise, those that intuition is clear, then it becomes easy for us to uh, refactor. When there is a bug, we can fix it very easily. Observability becomes easy, and there is an accountability also. So even if it is the LLM is doing something, we would know which model or because of what reasons the model is arising the ambiguity or fixing that ambiguity in a particular way, right? Um, Cognitive load is another big topic to talk about when we involve AI systems, right? AI powered systems, uh, especially in vibe coding. You send a prompt, it writes code, and then something fails. You say, okay, go back. There is an error. Go back and fix it. It goes in loop on and on. At the end of the day, you'll delete the code and write it yourself. That's a better thing to do sometimes because we are spending a lot of our cognitive energy, right? So when we have these invariants, ambiguities, boundaries defined in the system, whether it is in the prompts or in the, let's say, PRDs that we started using it again after a long time, when these are defined explicitly, then the cognitive load comes down and we have the accountability, right? Not the models, not the AI. And going back to observability, like we'll be able to reason about it. So once we know all these things, we can constrain the output of the model. We can actually guide it to give us a good output, whether it be a normal prompting and response or using LLM models inside the system itself, because they're going to communicate with each other, right? The models will be communicating with each other. So that can be streamlined, thinned so that they communicate well, and we can also reason about that communication, right? So we have a and we can have deterministic validation layers. Again, more words for testing and encode invariance in tests, adjust the temperatures, and check whether the output is coming as expected or not. So that's what I was that that was a thought that I had. Like, uh, where should we where should we focus when working on AI powered systems? Whether it's when using AI like Cursor or Claude, Claude Code or Copilot, we should be very cognizant of what we are doing and document everything, right? Whether the prompts or the PRDs and whatever it is. And we have to give more information, save more information that will help us in actually uh, deciding the boundaries. In turn, that will help us in reasoning where the ambiguities are arising, how it is solved, and that's how the intelligence is distributed. I mean, our intelligence is distributed, right? So it can be in the prompts or in the code or in the layers in between or in the output response that is coming in. Okay, we talked about all these ambiguities coming in where we have to, but where it is being solved, that is that's for another talk actually, because there are many uh, components now in the AI systems. There's now prompts, there's models, um, and more components that I wanted to talk about, but that will become itself become another talk. So probably in the future I can talk about it because it involves a um, lot of information to share about how prompting, how to prompt well, how to ingest context, how to do context engineering well, so that we can drive this uh, AI-powered systems well, right? Yeah. So that comes to the end of the talk. Thank you. Any questions? So so the question is there any framework to streamline the constraints on invariance, right? So there are many frameworks actually, and those frameworks are also evolving. Um, Initially, there was a very small utility called Task Manager, where you provide the PRD, it can create tasks for you in a text format in the wherever you're working, and then you can do a check mark for this task is done, this is done, this is done, kind of. Now there are others. One is BMAC method. The other one is spec-driven, spec-kit by Copilot, GitHub Copilot. So that is one other framework that helps in um, streamline these constraints. Constraints are nothing but what the system should do and not do, right? And the PRDs are the one way of doing it, but there are several other ways of doing it. Yeah. So the question is about there are many layers now, and ambiguity where is it is getting pushed, how to handle it. Correct? Okay. So yes, so the ambiguity is not going to go away. It's going to be there. We we are just going to defer it, right? Until to the edge of that system, particular component, and then handle it. Does that clear? Right, right. Yes. Yes. Yeah. So how do we solve that is actually we have solved it earlier also. We just have to bring that perspective to the AI era. For example, in uh, if you have worked in functional programming, right? Um, I'm a proponent of functional programming, right? So you push all the impure functions to the boundaries, right? You won't have those uh, impure functions in the core of your system. So what is impure functions? Anything that talks to the outside, mutates system outside of its own world. That's an impure function, right? Like an IO or talking to another resource, or sending information to other resource, saving it there and getting an information. That's an impure system, right? So you push it to the boundaries. You won't keep it in your layer. For example, in the onion layer architecture, your core is going to be very pure. Your business logic is in the core. Saving to the database, sending the information to the other systems, that lies in the ports, right? And then you write adapters to those ports, and those adapters take care of handling the impurities, right? Or the impure functions or the mutabilities, right? So we have to bring the same perspective here. Uh, the more clarity that we have in the prompts, how the models behave, how we are thinking, and how we are feeding that information to the models, then it becomes very clear for us. Then it will become very clear for us. So how? So in the pre-AI era, what we used to do, we used to think a lot before writing code. That's why it is always in our mind. And then we translate that information into code and we test it and we push it. Now we are not thinking in the code level. We are thinking at the prompt level, right? We are thinking about what prompt should I give so that it will create this output. Then we have introduced one more layer. And the models introduce one more or two more layers in between. That is the implicit variant that I'm talking about. We don't know. It is there, but we are not aware of it. We don't see it. It is in a latent space. It is in a mathematical space. It is in one world. So the more understanding we have about that, it will be very clear for us to where to look for those things. Probably the first place will be the prompts now, because prompts have become the first class artifacts now. Along with the source code, we are storing prompts also, versioning it, keeping it, and probably the entire chat history also. Any more questions? Okay. Thank you.